Okay. Hi, everyone. I'm Catherine, and today I'm here to make my pet peeve into your new pet peeve. So I study supernovae, which means I blow up stars on computers, and I was having a lot of trouble getting my star to blow up. So I went and started reading papers, trying to figure out what's going on, try to get some ideas. And the papers make things sound pretty straightforward. They're like, okay, so we start with a star model. So essentially that's a 2 or 3-dimensional grid, and each grid cell is given a density, a temperature, a pressure, and some chemical composition. So that's your initial star. And then you put that grid into a physics simulation, which uses equations of hydrodynamics to move the fluids around, nuclear burning to fuse elements together, and gravity, that's everywhere. And it basically makes your star blow up. And once your star is done exploding, you add up the energy across the grid to tell you how energetic your supernova was, and you compare that with observations to see how good your model was. And that's fine, but I really wish that all these papers had a section called problems that you'll definitely run into and ideas on how to solve them, because I was having so much trouble. And I'm definitely not the first or last person who's going to run into trouble. So this started with our initial conditions. In order for a hydrodynamic solver to work on a grid, you need to have material on every grid cell, which means that instead of the vacuum of space, you need to put a placeholder material, which we very scientifically call fluff. And I found that by changing the density of this fluff would actually change the geometry of my explosion. And this was bad because the fluff isn't actually really there in real life, so it shouldn't affect my explosion at all. So that was weird. The second thing that we ran into was a problem with our equation of state. And you can think of this like a black box where you input a density and temperature and it spits out an energy. So this plot here is showing you the results from our equation of state. And you can see that at low densities and temperatures, our equation of state gives you a negative energy, which does not make any physical sense, right? That is confusing. And it turns out that what was happening was our equation of state is meant to describe a fully ionized gas, but at those low densities and temperatures, the atoms were pulling the electrons back so that it's not fully ionized anymore. So that assumption, and now your equation of state is not valid in that region. Last but not least, and probably most fun, we found that some of our simulations re-exploded. So they would explode once and release a little bit of mass. Then you'd have this part left behind that would recontract and re-explode. So that was really fun. And the reason I'm telling you all of these challenges is because we all work with interdisciplinary codes. And so the challenges that we face are helpful, not just for our field, but across scientific disciplines. So like my code, I'm using an astrophysics application, but people who are doing experiments with fusion or modeling nuclear explosions also use it. So I hope that in your next paper, you show your interesting results, but you also make it helpful for others. Thank you.
Both of these big kind of worlds.
Oh yeah, absolutely.
So how would you, I guess there's this saying in the software development industry, eat your own dog food. So what does your next paper look like?
Oh, well, Alan will tell you. My next paper is obnoxiously long. That's okay. It's in astrophysics, they're long. So I have put all of these issues into my paper throughout. So wherever I ran into something like this equation of state, I basically say, oh, here's this issue. I found it in this unrelated or paper and I cite it and I say, hey, this is a problem, and kind of leave it open-ended, like we have to figure out how to solve this problem before we can move forward. So I don't know what the reviewers would think, but I'm trying to be a helpful scientist in the future. Yeah. That's a great idea. Yes, I could share my parameter file publicly. That's a great idea. I didn't think of that. So thank you. So good. I know I'm not trying to start a movement. I'm just saying. Yeah.
We're on the train already.
Oh yeah, sure. So I'm working with low energy supernova. If you want to get jargony, they're called type 1AX supernova. So normally what happens is you have a deflagration. That's kind of what happens in your car engine. So you have a slow subsonic burning, and that goes through your star. And if you have a really energetic supernova that transitions to a detonation and blows the whole star apart, right? And then you don't have this problem because all the material is just flying off into space. But in this case, we just have that deflagration and it never transitions. So you have a bunch of material slowly moving away from the center of your star, but most of it is still left behind. And that is so massive that it starts recontracting. And that contraction kind of sends a shock into the center, which starts the detonation there. So that's why that's happening. But the dynamics of that is like really complicated. And, you know, my code is not meant to model this. This was like, oh God, what's happening? So
like the future work, shit that went wrong, like what is the title of the science?
Oh yeah, that's a great question. So I know that every field is totally different how they handle things. So I don't know if it should be something like a supplemental, like an appendix at the end, or its own section, like here are challenges that I had with the simulation. Because a lot of papers, like we all have this fluff material, but nobody tells you what they set the density, pressure, temperature to, which is not helpful, right? So like you could either put that in your method section where I put, we set it to this, or like Owen said, we could share our parameter files. So I guess field specific, it might look a little different because I don't know how papers are structured in different fields.
I gave this talk at the and I played all the stuff that didn't work.
That's so cool.
Like, whoa, it didn't work. So isn't that whoa?
Yes.
A little bit or on what Owen said, I would just say that I think that increasingly people are putting the parameter files or all of that available. I think what you're saying is actually one step further, which is that unless you know why they put that,
right,
you don't know all the people they tried to do for. And if I found information that appreciates the water site here, and there's literally found that not online, and so that's a mental block that I think people do. I think we're now like, well, obviously.
Right, yeah, the stuff that doesn't work is sometimes more helpful than the stuff that does work. Yeah, that's so true.
Quickly.
Yeah. Awesome. Wow.
Good.
All right, hello. I'm Sully. I'm a PhD student at the IACS Skill Lab, supervised by Dr. Barbara Chapman. I'm here to talk about using OpenMP to accelerate scientific applications. So this large figure on the left-hand side shows the performance gap between a dual socket CPU and a GPU, a single GPU, is getting larger over the past 10 years. And the OpenMC team, OpenMC is the Open Monte Carlo simulation code. Actually, I don't know what he's doing, but anyway. So yeah, the OpenMC team measures the gap. And as we can see from 2016, that gap is getting larger. And there is no chance for the best CPU of the world that can catch up to the performance of a single GPU. So that is a